Today we're going to continue talking about Newton's laws of motion, and specifically today we'll be looking at Newton's second and third laws. So the question that Newton was really trying to answer was, what causes acceleration? And the first thing we want to remember is just what do we mean by something accelerating? And if something is accelerating, it's doing one of two things. It's either speeding up or it's slowing down. So remember that in physics, when we say acceleration, we mean either speeding up or slowing down. Well, it turns out that a net force on an object will cause it to accelerate. And if you think about this, Newton's first law really kind of tells us that, because Newton's first law says that if an object does not have a net force acting on it, then the object will not accelerate. In other words, it will continue at a constant speed or it will stay at rest. So if there is a net force on an object, then the object is going to accelerate. And the next question we might ask is, does the same force have the same effect on different objects? And you already have a sense of that too, because if I said, okay, I want you to exert a force on a baseball to get it accelerating, in other words, to speed it up, to throw it, that would be one thing. If I said, go out and exert the same force on a stationary car, are you going to get that car to move as fast as you could get the baseball to move? And obviously the answer to that is no. And so it turns out that not only does the acceleration depend on how much force we're applying, but it also depends on the mass of the object. And that's what Newton's law says. So here's Newton's second law. And it simply says that the acceleration of an object is equal to the net force on the object divided by the mass of the object. Now, when we measure force, as we've talked about, we measure force in newtons, and mass is measured in kilograms. And remember that acceleration is in meters per second squared. So if I have a net force acting on an object of mass m, then that object will accelerate as given by this formula. Now oftentimes you'll see this rearranged and written this way, that the net force on an object is equal to the mass times the acceleration. And it's convenient sometimes to use it that way. But it's important to think about Newton's law this way, because force causes acceleration. And so that's what's implied when we write it that way. All right, let's take a look at a problem and test this out. We know that acceleration is equal to the net force acting on the object divided by the mass. So a toy car with a mass of 2 kilograms is pushed from rest with a force of 6 newtons. What's the acceleration of the car? Well, in this case, the only force acting on the car is that force of 6 newtons. So that's the net force. So that would be 6 newtons. And the mass of the car is 2 kilograms. And therefore, the acceleration is 3 meters per second squared. Now remember what meters per second squared really means. It simply means the number of meters per second that the object will either gain or lose in each second. Meters per second per second. So let's take a look at something that involves that. And this is kind of a review of our basic understanding of velocity and acceleration. If the car starts from rest, how fast will the car be moving after 5 seconds? Well, if it starts from rest, when time equals 0, in other words, right when the motion starts, we kind of start our stopwatch, the velocity would be 0, and therefore after 1 second it will have gained 3 meters per second. After 2 seconds it will have gained 3 additional meters per second, so it'll be 6 meters per second. And we can keep going with this. So after 3 seconds it will have gained another 3, so now it's moving at 9 meters per second. After 4 seconds it will have gained another 3, so we're at 12. And finally we get up to the fact that after 5 seconds it will be moving at 15 meters per second. Let's take a look at another problem. This one says a toy car with a mass of 2 kilograms is pushed from rest with a force of 6 newtons. The force of friction on the car is 2 newtons. What is the acceleration of the car? Okay, so Newton's second law, again, tells us that the acceleration is the net force divided by the mass. So in this case, I've got my little toy car here, and we've got a force of 6 newtons trying to make the car go. The force of friction is 2 newtons. Friction always opposes the direction of motion. So the net force on the car would be 6 newtons minus 2 newtons. So the net force would be 4, divided by 2 kilograms. And let's see, 6 minus 2 is 4, divided by 2. So the answer would be 2 meters per second squared. And that would be the acceleration. The next thing we want to look at is Newton's third law of motion. And in order to understand Newton's third law, the first thing we have to understand is that forces always occur in pairs. And if you think about it, you can't exert a force on some other object without that object exerting a force back on you. So for example, I push on the wall pushes back on me. When hitting a baseball, the bat pushes on the ball pushes back on the bat. You can actually notice this with a wood bat. You'll see little dents from the ball on the bat. So the ball exerts a force on the bat exerts a force on the ball. Right now, if you're sitting in a chair, your weight pushes the chair down, the chair pushes up on you. So forces always occur in pairs. You can't have one object exert a force on the second object without that second object exerting a force back on the first. Well, that's what Newton's third law is all about. It turns out that not only do forces occur in pairs, but those forces are equal. So here's what Newton's third law says. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So in other words, if I'm standing next to the wall here, and I kind of lean over, okay, my arm's a little long, I understand. I've got long arms. So I'm leaning against the wall, and I'm exerting a force on the wall in this direction. Okay, so that's one force. Well, the wall is exerting a force back on me. And those two forces are equal in magnitude and opposite in direction. That's what Newton's third law says. Sometimes Newton's third law is stated this way. To every action, there is an equal and opposite reaction. And when it's stated this way, and by the way, this is actually how Newton said it, action and reaction simply mean force. Okay? So, to every force, there's an equal and opposite force, is the other way to say that. All right, let's take a look at an example of Newton's third law. When a mosquito smashes on your windshield, which experiences more force, the windshield or the mosquito? Well, according to Newton's third law, the forces are equal. Okay? Now, if you ask most people that question who haven't had a physics course, they'll say the mosquito experiences the greater force. After all, the mosquito gets splattered on the windshield, and you know, it doesn't seem like anything happens to the windshield. The thing to realize, though, that the forces are the same, but the accelerations are very different. So, in other words, the mosquito experiences a much greater acceleration, and that's the result that we see. And the reason for that is, if we look at the acceleration of the mosquito, the force that the mosquito exerts on the windshield, and therefore the force that the windshield exerts on the mosquito, is very small. So I'll just represent that with a little f here. Now, the thing is that the mass of the mosquito is also small, and so the acceleration is big. Okay. If we look at the windshield, in other words, the car, because the windshield's attached to the car. So really, it's the car that we're interested in. If you think about what happens to the car, the force is small, but the mass of the car is big. And so the acceleration of the car is very small. In other words, the mosquito's direct velocity changes dramatically. It was flying one direction, hits the windshield, and now it's going the other direction. So it had a big acceleration, and therefore the little mosquito gets destroyed in that situation. The car, basically it's going along, it hits the mosquito, it's like nothing happened to it because the mass of the car is so big compared to the force. So the important thing to understand is that yes, the mosquito exerts the same force on the car as the car exerts on the mosquito, but the results are very different. Let's take a look at one more example of this. A rifle fires a bullet. What are the action and reaction forces? Okay, so what are the two forces acting? Here's my rifle. And when the bullet gets fired, the rifle exerts a force on the bullet. So there's one force. But the bullet has to exert an equal and opposite force on the rifle. And so that force would be back in this direction. And those forces are equal and opposite. Now, that, by the way, is why if you've ever fired a gun or you've seen someone fire a gun, you'll notice that the gun kicks back. The gun goes backwards a little bit when you shoot it. And that's simply because the gun exerts a force on the bullet, but the bullet exerts an equal and opposite force back on the gun. And so the gun moves backwards somewhat as the bullet moves forwards. Now, again, which has a greater acceleration, the rifle or the bullet? Well, the bullet has a much greater acceleration because, again, for the bullet, there's a pretty big force on the bullet, but the mass is small. And when you take a big number and divide by a small number, again, you get something that's big. On the other hand, for the rifle, although you still got that fairly big force, the mass of the rifle is much bigger, and so that's small. Now, one of the things you could think about is, would it be a good design if the rifle and the bullet had the same mass? So would that be a good idea? And of course, the answer to that is no, because if they had the same mass, then the rifle would come back just as fast as the bullet moves forward. Okay? And obviously that would not be a good thing if you're the person firing the gun.